Okay, let's get started. Okay, you three. So, what we're going to start today is continuing these exponential functions and focusing on transforming them. And just a little preview, we've actually kind of started this already when we did our adding a number and dragging it upwards or minusing a number to the function and pushing it downwards. So we're going to just kind of do that again and add on a few more different rules. A quick reminder announcement for today is a reminder to complete this week's homework. At least give it a shot. Don't give it a try. Don't put it off because if you wait a week or two, it's going to be even more confusing than if it's fresh in your mind from today. And here's those assignments. Just a reminder, Tuesday we had the 4 questions from page 11 of the first tutorial called Graphs of Exponential Relationships, just the page 11. And in order for me to see your work, I do need you to submit it at the end. So it won't be complete. I'm not asking you to do the whole tutorial. You may, for extra like support, that probably wouldn't be a bad idea. But all I want to see is page 11 done. So make sure to submit. Use the submit button when you're done with those 4 questions. Otherwise, I won't be able to see your work. So even if you did it, make sure to go back in and submit it. It should have saved it if you hit the little submit button, but I mean the submit button at the end. And then yesterday we did the mastery test for that first lesson, graphs of exponentials. Today we're going to be doing the second, like official lesson in Admentum. Morning, Tira.
Good morning.
All right, you 4. Let's get started. So here's a little overview of what we're going to be doing. Like I said just a minute ago, we're going to be focusing on transforming our exponential functions. And what does that mean? Transforming for us in math means taking the original function, quote unquote, the original function, for example, like y is equal to 2 to the x, the one we've been working with a lot, and then changing that by shifting it up, shifting it down, shifting it left or right. And then also it includes stretching it vertically or stretching it horizontally. So kind of like pulling it up and down at the same time or pulling it left and right at the same time. So these two at the bottom, these stretches, these will warp the shape. The first 4, shifting it up, down, left, or right, these keep the shape the same, but just move it, kind of move it over left, move it over right, up or down. But it will kind of warp and be slightly skinnier or wider or longer looking than the original. So just keep that in mind. And so how I set this up was we're going to go over each like 2 rules at a time and then do 2 examples and then do the next 2 rules and then the next 2 examples and so forth. So let's start with shifting it up or down. Oh, before you know what? Sorry. Before we do that, let's look at some pictures to just kind of get an idea before we look at the rules of what the graphs look like doing these different transformations. So on the left, same function as we've been using a lot, 2 to the x. Y is equal to 2 to the x power. So that'll be our original function for this example. And now look at my new graph in the center of the screen there. What does that look like happen to the original? Anyone want to take a stab at that? If it's a shift. So the shape didn't really change, but we did something to it to transform it.
Wait, what was the question?
Sorry, thanks for asking. Let me rephrase my question. Does it look like my new graph in the center of the screen was shifted up, shifted down, left, or right?
Hmm, it looks like it was shifted maybe right.
Well, uh, if we're considering this one on the left as quote unquote original, meaning that's our starting position, it's hugging the x-axis like our exponentials do right here where I'm making it red. That's what I mean by hugging it, kind of approaching it, getting close to the x-axis. Looking at the new one in the center, what does it look like that's approaching and getting flat or hugging? It looks like it's approaching up here, right? Compare that to the original. See something in the chat. Sorry, one moment. Levi. Oh, sorry. Levi said shifted up. If we compare the new graph to the one on the left, which we're going to call that our original, it does look like this one was shifted up. And here's another way we can kind of tell. Now, forgive me because I know these graphs are probably a little small for your view, but let's focus on a couple key points that we could find and then kind of compare the starting point to the ending point. When I say ending, I mean the new graph. So what I mean is let's look at the y-intercept because that's an easy point to identify. It's crossing at 0, 1. And then here's another one where it's going through the whole numbers at 1, comma 2. There we go. And now if we kind of look for where it's crossing in those whole numbers on the new graph over on the right, I see the y-intercept is right here. What is that? 0, 3. And the next spot, point where it's crossing whole numbers looks like it's 1, comma 4. So kind of if we compare those points, the y-intercept started at 0, 1, and now it's at 0, 3. 1 to 3 kind of suggests that we pulled that spot upwards. And then same for the 1, comma 2 point. It transformed to 1, 4, and that kind of implies that that 2 was pulled up to 4. All the points on the original graph were shifted up from their like original spot. Tira and Levi, thank you both for trying that one with me. So another one, I'm going to put another one on the screen there. Same original on the left side. Take another guess, your best guess at what you think may be happening here. Does it look like my original function was pulled left, pulled right, or pulled up or down? Any ideas?
It looked. Oh, sorry.
Why don't we have I'm not sure who was first. Alphabetically, we'll say Anaya first and then Tira, please.
Okay.
I was going to say we shifted down.
Shifted down. Thank you, Anaya. And Tira?
I was gonna say the same thing
High
because
five.
it looks like it's going down towards like the negative numbers.
For sure. Find some landmark to kind of compare. I used those 2 points last time, and also we can use like the flattish looking part. And I think that's what you're focusing on, Tira, is the flat part. It's going down this time. Instead of at the x-axis, it's down at -2. And if we did it with the points, we should see the same thing. Good. Thank you to both of you. Shifted down. And now let's look at the left and right shifts. These are a little harder to see, but I'm just going to put them up here, not make it a mystery. Just take a moment and just compare and soak this in visually. So I haven't changed the shape of our original function, 2 to the x. All I did was shift it up, down, and then at the bottom we see a left shift and a right shift. So if we kind of look at where the bend is, right? Let me change my color. Where the bend goes in this exponential. I'll change to purple to show this off. So kind of this elbow, this like bending spot, you can use that as a frame of reference or a landmark to track. So looking at my left shift photo graph, the bend is happening left of the original, and then looking at the right, the bend is happening right of the original. So that's another way to kind of just orient yourself and figure out, what am I looking at? Did this thing shift up, down, or left, right? In the problems we do today, and everything in the Edmentum, they're going to give us an original function, and then we have to figure out either the equation for the shifted version, or maybe the picture for the shifted version, like these. So I thought we'd start by kind of just looking at all of them to start thinking about what the pictures look like when we graph them. If you want to take a picture, or if you're copying down, I'm going to wait for 10 more seconds. And then I want to really quick look at the stretches, stretching vertically or stretch horizontally. And then we'll get into the technical stuff, and we'll look at some examples for each one of these. Today, I timed out and paced everything I want to show you and do with you. So I'm hoping we can do it all, and I won't run too late like I have been. And we might even end a little early. So let's see how this goes. So here's our stretching vertically and stretching horizontally pictures just to start with. So again, on the left, I haven't changed any of the original. Here's our 2 to the x original function on the left side. And if we compare that to these stretches, look at the stretching vertically with me. This one, if we just were looking at the bend, the elbow shape in purple, you might first think for the stretch vertically that this was a horizontal, or I'm sorry, a leftwards shift from the last screen. However, you also should notice, oh, it's got this crossing point. The y-intercept is much higher than normal. So that is a little clue that either this is a shift left, or maybe it could be a vertical stretch based on this picture. So it just helps to narrow down kind of and eliminate some options and determine what options could this be. And then look at the horizontal one with me. This shape is, I made this one a bigger number on purpose when I stretched it. So I purposely tried to make it very different looking in its shape. What happened is the original, I'll do that in purple, looks something like this, crosses at 1, and then should kind of go up like this. So we took our original and we stretched it outwards, pulling all these points left and right, not messing with their heights, but just pulling everything leftwards and rightwards. And what happened for the above picture, the stretch vertically, is we took the original and stretched everything upwards and downwards by some factor. So these ones can be tricky. And just so you know, I wanted you all to know that in the Edmentum work that I found today, looking at our mastery test, the good news for us is that all the ones that talk about stretches, horizontal or vertical, they tell you that in the problem. So it's really going to be a matter of just working with the rule. So we'll look at that in a little bit. But they don't make it too difficult as trying to make you figure out, like, is this a left shift or a vertical stretch? They tell you that it's going to be a stretch vertically. So that's nice. So let's look at the 2 rules for shifting up and shifting down. Now, if you think back to, if you can remember back before Christmas, and I think even before November, Thanksgiving, we did transformations for straight lines. And I know that was a tough a subject. The good news for us today is that all the transformation rules we did for straight lines, linear functions, are actually the same rules that we're using for our exponentials. So here's our shifting up and down rules, and I did them as examples with an actual number. So first we see f of x plus 3. We see it adding some number, adding the 3. And what this means, we're adding 3 to the y values only. So if we had an original graph, f of x, this f of x, think of that as like the original. And then if we're adding something like this 3, that means we're transforming it by pushing it up 3 units. Shifting up 3 units. Is the purple too dark for you folks to see? Should I go back to red? No?
No.
No.
Okay. Thank you for your feedback. And then let's compare that to what we see below, f of x minus 3. So if we see a minus some number, then that's our original f of x. And the whole thing is being dragged or shifted down 3. So I like starting with these because everything is taken at face value. It looks like plus 3. Okay, so that means I'm just pulling the whole thing up 3. Or minus 3, likewise, I'm pushing it all down 3. Just note that if we're dealing with the points, and we're going to do an example with this in a moment, if we're dealing with the actual points of the graph, then here's how we deal with that. We add 3 to the y values of the original, and then that gives us the new transformed point. Or likewise, subtract 3 to the y values only. So if we have our original plus or minus a number, that means we're shifting up or down. And just to hopefully tie all this together, I'm going to put the pictures up if we did this transformation. So above, here's, again, the same parent graph I want to start with as our original, quote unquote. We've been working with this a lot. So it's just an easy one to kind of keep as our starting point. So 2 to the x power. Now, if we were to do a transformation of plus 3 to this, f of x plus 3, like in my example, it's the same exact function, except everything's gone up 3 units from wherever it was before. And if we want to track some specific points, looking at the y-intercept for the original above is 0, 1. And then the y-intercept for the new guy is 0, 1, 2, 3, 4. And lo and behold, to track that change, it's adding the number 3 to just the y value. X didn't change. It's still 0. And if we do a subtract 3, that'll look like this. So that's what I like about the shifting up or down or left and right. It doesn't change the original shape. So the curve is actually the same exact curve. We could layer all 3 of these right on top of each other and it would match up perfectly. What's changing though is where it lives on the graph. That's it for shifting up and down. Are there any questions right now about either of these? Please, comments, concerns, questions?
Yeah, I had a question about the second one,
Please.
fx plus 3.
Yeah.
So you said we're adding the 3 to the y value for fx equals 2x?
Correct.
Okay.
Let me show you a quick example of what that means. Maybe I should have done that before, but a good question. So for instance, we look at our original graph, that's our top one here, and I already found 1 point, 0, comma 1. So if I started like this, I'm going to show it in red. On f of x, 1 point is 0, 1. And then we're told to do this transformation f of x plus 3. This is I'm going to label it the transformation. So in my little rule above says add 3 to the y values only. So if we did that to the point 0, 1, I add a 3 to just the y value. And what does that give us when we're done, messing with it, transforming it? 0, comma 4. And sure enough, we see that spot on the actual black line, the function line over here for our transform, 0, comma 4. And if you wanted to check any of the points that existed on the original, add 3 to them to just the y value, it lines up with the new one in f of x plus 3. And likewise, Tira, if we do it with the minusing version below, the same thing is working there. So originally, back to the top picture, we've got 0, 1. So I'll do the same thing here. On f of x, we have 0, 1. We transform by doing f of x plus 3. And that means add 3 to just the y, or I'm sorry, darn it, subtract this time. So it means f of x minus 3 is the transformation for this one. So then we're minusing 3 from whatever that original point was. So 0, 1 minus 3. And what is that? 1 minus 3 is negative 2. So 0, negative 2. And sure enough, on the black graph, the black line, the function line, we see 0, negative 2.
Okay, I get it now.
Does that help?
Thank you. Yeah, it does.
Awesome. Good question. And we can see that these rules I'm going to show you will correlate to the picture itself for all of them. So after this page, I want to do some examples from the mastery test, and then we'll look at the remaining 4 rules and doing the rule to like any given point to check, like I did with 0, 1. It'll work for the new transformed graph. So it's useful to do that. All right, so let's check out a problem from the Admentum that has to do with shifting up or down. So they say consider function f below. F of x is equal to 4 to the x. That's our clue right here, that this is an exponential, minus 6. So this whole thing, this whole f of x is the original. So it's not just the 4 to the x, it's actually 4 to the x minus 6. That whole deal is our original. Now they say determine function g, which is created by shifting the graph of f up 5 units. Up 5 units. So shifting the original up 5, your mind is already saying, okay, whatever the original looks like, it's going to get pulled up 5 units like this. So how do we deal with that with our function in like its formula like this? Well, take f of x. Up 5 means plus 5 to the outside, like this, like we saw on the last page. And if I were to substitute in, f of x is 4 to the x minus 6, right? So if I were to kind of swap that in, we've got some like terms here that can combine. Negative 6 plus 5, that leaves us with negative 1 or minus 1. So function g, which is the transformation of function f, would be this 4 to the x minus 1. Whatever the rule is or the transformation is that they're like telling us or presenting us with, in this case, it was up 5 units. All we need to do is basically kind of apply that plus 5 to the right part of the original function. And for up-down shifts, it just means adding the number or subtracting the number right to the original function, like I did here and here. Okay, let's see. Let's look at another one about a shift, up or down. Now, this time they're not doing a graph at all. They're giving us the table. So this is like what Tira asked about a moment ago. The function f is given by the table of values. So this top table is the function f, or really it's just a few points from function f. Our x's and the f of x is kind of like our y. Same thing. We've been talking about that for a while. If f of x is shifted 5 units down to obtain g of x, which table represents the function g? So one of these tables below is taking the original and pushing the whole thing down 5 units. What is,
Josiah,
oh yeah, go
what,
ahead. Go ahead.
sorry. So if it says down, wouldn't that mean that it's negative numbers? Like, wouldn't that be the keyword?
It is. It's going to be, and the down goes with negative or minus.
Okay.
So that's the key word. You're right. Down means we're going to be going from whatever we started with and apply this right here. Back to my the rule page. Subtract 3 to the y values only. It's kind of like all the x values stay where they are, but the thing gets pushed or shoved downward however many units. Only to the y's. Doesn't change the x's. So think about it this way. The x numbers from the top table stay the same, but we're going to do -5 to all the stuff in the y table or the f of x table. So if we do that, what do we get for those new f of x numbers? So looking at the first point, 1, comma 5, but we do -5 to the y number, the f of x number. So 5 minus 5, 0. 2, 7 originally, but we're doing a downward shift of 5. So we do that -5, 7 minus 5 is 2. And then 3, remember x stays the same and we're just applying a -5 to the y number. So 11 minus 5 gives us, what is that, 6? And then 419 is going to transform to 4 comma, what is that, 19 minus 5? 14? So because they told us, Tira pointed out the keyword was down, and we associate down with negative or minus, right? So down 5 just to the y values. Why is it just the y values? Because of down. If it was left or right, then we're going to be dealing with x values, and that's what we're going to look at next. And then, so I did the table on the top, and then obviously we would just scan through and find, okay, which one is most like or just like what we found. Looks like C works. 1, 0, 2, 2, 3, 6, 4, 14. Good.
Josiah, can I take a picture real quick?
Yes, very good. Take a picture. And then we're going to look at the left-right shifts. And I've got it formatted the same way. So here we go. Are we ready? Tira?
Yes.
Okay, thank you. Here we go. So here's shifting left or right. And for all these examples today, I thought I would stick with the number 3 just to keep it consistent. So 2 rules here. The top one, the first one rather, is shifting left. And below we have shifting right. Now things are might get a little weird here. Hopefully, you remember back to what we did for straight line transformations. When we were doing straight line transformations, we do everything for the y at face value. And whenever we're doing a change, a transformation to x or left right, we do opposite of what it looks like. So for a shift left, you're going to see that as the transformation, the plus or minus number, inside the parentheses with x. If it's inside the parentheses like these ones are, that means we're doing the change left or right. Shifting left or right. And we do it opposite of what it looks like. So for a shift left, f of x plus 3, this means we're actually subtracting 3 to the x values only. If the change is a horizontal change, left or right, it's opposite of what it looks like. So if you see on the paper or on the computer f of x plus 3, we need to remember, okay, it's inside the parentheses, so that's our clue that it's a left or right move, shift, transformation. And whenever it's inside the parentheses, it's opposite of what it looks like. So instead of plus 3 to everything, we subtract 3 to the x values only. Below, shifting right, these are shown as minus 3, x minus 3. And then that means we add 3 to the x values only. It is just like when we did it for linear transformations. Horizontal, and I'm going to add this at the top. Make sure to put this in your notes as well. Always do the opposite of what it looks like for horizontal shifts. Opposite of what it looks like. Actually, we'll leave that. So if you see it's inside the parentheses, then right away we should be thinking, okay, this is left, right, not up, down, and it's opposite of what it looks like. So it's going to take some practice to get used to this. So again, I have the pictures to go along with this. At the top, same starting function, 2 to the x. Now let's compare that to the shift left. So I took the original function and went leftwards with all the points, 3 units. So for instance, let's track the y-intercept from the original. So looking at the top, same point is 0, 1. We've used that one a lot. Hope you're not getting tired of it. And if I took 0, 1, let's do this math in the middle of the screen. 0, 1 is on the original. My transformation is f of x plus 3. It's inside the parentheses, so I do opposite of what it looks like, and it's a left-right move. So instead of plus, which usually I think adding, moving rightwards, right, getting bigger, we're going to do the opposite, which is minus 3 to the x value. So the x value is 0, not 1. 0 minus 3, comma 1. And if you simplify that, it's negative 3, comma 1. And let's check to see if that exists on the new graph. Negative 3, 1. So that's left 1, 2, 3, up 1. That's right here. So this point is my original transferred over, 3 units. 1, 2, 3. Now for the rightward shift. That y-intercept of 0, 1 was transferred rightwards this time. 1, 2, 3. And if we try the math for the rule, same starting point. So on f of x, we've got 0, 1. I do my transformation. This time it's f of x minus 3 in the parentheses. So I'm going to apply the opposite of minus 3. which is plus 3 to the x value. So 0 plus 3, comma 1, and that leaves me with a positive 3, 1. And we see that positive 3, 1 on the black graph on the right side, 3, comma 1. So I realize that these are trickier. And like I said, I think practice is probably the best medicine for this. So to finish up your notes or take a picture or let me know if you need more time. And then we're going to look at 2 examples of left or right shifts. Here we go. So from our Edmentum, consider the function f of x equals 2 to the x and the function g of x. So again, I like that they're using our much used parent graph of 2 to the x. And then below we have g of x equals f of x plus 4. So this is a transformation. We know it's a transformation because it's like it looks like f of x, but they're changing it with a plus or a minus inside the parentheses, right? If it's inside the parentheses, we go back to that golden rule for us. In the parentheses, that's our clue that it's a left-right, and we do opposite of what it looks like. Remember that. Opposite, do the opposite of what it looks like or what it seems. So the change they're giving us is plus 4. So usually I would say, okay, plus 4 means we're adding 4, we're getting bigger, we're going rightwards. But if I'm supposed to do the opposite, that means we're going to go leftwards. Or the rule would be subtract 4 from all the x values. Oh, I don't know what's wrong with my grammar today. From all x values. Forgive me. Now we get to the question. How will the graph of g of x differ from the graph of f of x? Basically, what's the physical change from our starting f of x equals 2 to the x to this new one, g of x? So we've got to read through these and do our best to navigate and figure out which one makes the most sense to what we know the rule is telling us. So the rules, looking at my red again above, before I even look at A, B, C, and D, we know that this is a subtract 4 from all x values. It takes our original f of x and does the opposite of what it looks like because it's in those parentheses. So we're going to go not plus 4 to the right, but left. So it's shifting the whole thing left 4 units. And then we can look for that below.
So it would be C.
Nice. Yeah, it would be C. The graph of g of x, the new one, is the original f of x shifted 4 units to the left. So I have another example to show you, but really quick, I want to just go back to these rules. So here's the first ones we did, up and down. So just a quick reminder, if it's an up-down shift, the equation is going to be the change, the transformation, the plus 3 is on the outside of the parentheses. Notice that here, plus 3 on the outside, minus 3 on the outside. So outside, the f of x, like outside the parentheses, that's our clue, it's up or down. And then our left, right, the change is inside the parentheses. That's what's different about these. So just keep that in mind. Outside the parentheses means vertical, up or down. Inside the parentheses means horizontal left and right. And then also on top of that, inside the parentheses means opposite of what it looks like. Okay, one more here for left-right shift. In which direction must the graph of f of x equals 2 to the x, think of that as your original, be shifted to produce the graph of this? G of x is equal to 2 to the x minus 7. X minus 7, the minus 7 is our clue that there's some transformation. It's inside the parentheses. So in the parentheses means what? Horizontal or vertical? Up, down, or left, right? Anybody?
Inside the parentheses means horizontal, right?
Good. Yeah. So our clue right away, we know we're dealing with some horizontal. Okay. It's minus 7. So when it's horizontal, when it's in the parentheses, we have to remember to do opposite of what it seems. What it looks like, what it seems. So since minus 7, usually we think that goes left or down, right? Minus means negative or going down or left. But if I'm supposed to do the opposite, because it's in the parentheses, will that mean going rightwards, going leftwards, going down, or up?
I think it would go right because you're adding 7.
Very good. Yes. Thank you, Tira. Totally. So I'm trying to model for you guys how I approach problems like this. We have to be familiar with those rules or have them on our notes on a piece of paper that we can reference like a toolbox, and then examine what they're giving us, this g of x equation, and pick it apart and try to, one step at a time, one thought at a time, break it down and figure out what do we know and what does this mean? How do I apply those rules to this? So in the parentheses, that means horizontal. And then we have to think, okay, horizontal means do opposite. So first we narrow it down to left or right, and then we narrow it down to right because it's minus 7. Had it been this, 2 to the x plus 7, this would mean we're going left 7 units because it's plus. So we want to do the opposite. Very good, Tira. And are there any other questions on this example or the previous before we look at our last 2 rules for today? Okay. Okay, so now we come to the stretching. So for stretches, vertical or horizontal, instead of adding or subtracting numbers to our function f, you'll see it as a multiply. So let's look at the top line first. This is a vertical stretch. So if you have a number like 3, for instance, being multiplied to your function f, this means we are multiplying 3 to the y values only. A vertical stretch, pulling it down and up at the same time. So it's going to warp the original shape. And let's put up the example now for that. So again, f of x is the same as we've been using. And here's our vertical stretch 3 times f of x. This one might be a little hard to see just because the shape doesn't look too much different. But what's happening here is every point on the original graph has a 3 multiplied to its original y value. So when we see our original of 0, 1 on the y-intercept, where's the y-intercept on the new one below? It's at 0, 3. So what happened was our original point 0, 1 had this transformation applied to it. which means multiply 3 to the y values, which was 1. And when we simplify that, we get 0, comma 3. Now, 1's not that very interesting of a number. Let's see what happened to another point on the original. Here's another point that we can locate. It was 1, comma 2, right here. Sorry about that. All right, let's try the rule for 1, comma 2. So on the original, I've got 1, comma 2. We're going to apply the same transformation. That means multiply 3 to the y value. 2 times 3 is 6. So our final answer there is 1, comma 6. And let's check that out. Is 1 6? I know it's hard for you to see, but let's check that out on my transformed graph. So over 1, up 6, 1, 2, 3, 4, 5, 6. There it is. And it is in fact going right through 1, comma 6, right there. So you could do that for any point, not just the ones I've been using. I'm just looking for easy ones to check. Like the y-intercept was whole numbers, and so was 1, comma 2. When you get to the fraction stuff, the rule is still working there, even though it's hard to check those because it's hard to know what exactly, this point is right here, for example. That's some crazy fraction. Negative 1.5 up a half, maybe. It's hard to tell. But that spot is also being multiplied by 3. Okay, now finally, let's look at our horizontal stretch. So just being honest, full disclosure, this is probably the, shouldn't say hard, but the most complex, most maybe confusing of all the rules. So don't give up. We're all in this together. Here's what it looks like. This is the bottom rule in black that we're looking at, horizontal stretch. I'm using the number 3 for our horizontal stretch. So we see this in the formula as 3 times the x. Okay, no problem so far. But those same ideas apply to this. Horizontal, we just talked about this with the last Edmentum example. If it's in the parentheses, that's our clue. It's a horizontal change, transformation. And we do the opposite of what it looks like. So if you see a number like 3 multiplied to the x in the parentheses, then that means we're multiplying not 3, but the reciprocal 1 over 3 to the x values only. So let me write this down. When we do horizontal stretches for any multiplier inside the parentheses with x, what we're multiplying is the reciprocal. So that's how the opposite is kind of showing itself with the horizontal stretch. It's not negative, it's the reciprocal that we use. So that means it's like a flipped fraction. So for a whole number like 3, that turns into 1/3 that we're multiplying. And if they gave you a fraction to start with, we would multiply the flipped version of that to the x values only. Here's the picture on the right side of the screen if we were given that same transformation. So f of 3 to the x. Now I realize this is kind of hard, so I should have had Desmos ready to go for this. Let's compare our starting point and like an ending point. So if we use the y-intercept again, it's 0, 1. So on the original graph, right here, 0, 1 was our y-intercept. And if we were to have multiplied 0, comma 1, by this rule, it says multiply 1/3 to the x values. So hang on a second, I'm sorry. I'm sorry. I think I might have made a mistake on my picture. Because that should have brought it down to the 0 right there. It's pretty close, but it doesn't look like it's on the 0. The rule I put up is what we're going to use. I'm sorry, I think I just made a mistake on this graph that I made because it should be still at 0, 1. So my bad. Forgive me on that. We've only got a few minutes left. I want to show you some examples from Momentum that use these two rules for vertical stretches um, and horizontal stretches. So let's see. Here's the first one. Okay, an exponential function f passes through the points -2, -4, and 1, comma 10. So these 2 points are in the f of x function. Which 2 points would lie on the graph of the function g if g of x is equal to 3 times f of x? So here's the transformation they're giving us. 3 times f of x. Think of that as 3 times all the original points. It's out. The 3 times is outside the parentheses. Obviously, it's outside the f and the x parentheses. So that means it's a vertical stretch. And what do we do for vertical stretches? Multiply the number, the 3, to the y values only. So let's try that with the points they gave us. -2, 4. Using this rule should be multiply 3 to just the y values. So that's 3 times the 4. The -2 stays fixed, stays the same. 4 times 3, and that is 4 times 3 is 12. So we've got -2, comma 12. A quick scan of our options, there's only one there that has that point available. Looks like D because of this right here. -2. Oh, I made a mistake. It was supposed to be a -4. But that's correct. So -4 times negative times 3 would give us -12. And there's that point. Let's check the 1, comma 30 and make sure it's working there too. So the original point in F was 1, comma 10. Same transformation. 3 gets multiplied to just the y value. So 1 stays the same. 10 times 3 is 30. And sure enough, that is included in the D answer that we found earlier. So those 2 original F points got stretched 3 times bigger or higher than they were before, or lower in the -4 case. Okay, we have a few minutes, so let's do our final example. Okay, so here's another one I found from our Admentum today. The function f of x is equal to 7 to the x plus 1. So this whole thing is our original. It's coming to us with a plus 1 already. This original is transformed to function g through a horizontal compression by a factor of a third. What is the equation of function g? So they want us to straight up type it into this box below. You've all seen problems like this, most likely, throughout the year so far. So we know that horizontal compressions right here That means the change we do is going to be inside the parentheses. Or maybe we should say it's inside the parentheses, but it's also with the x itself, inside the parentheses. And that means for us with the x, not to the whole f of x, but just with the x. Another thing we have to remember for the horizontal changes, anything that's with the x, we don't do it at face value. We multiply it by the reciprocal, by the opposite of what it looks like. So if they want us to do a compression by a factor of a third, you might think, okay, I'm just going to multiply 1/3 to the x. But we need to do the opposite of that. So if we flip that fraction, the reciprocal is 3/1, or just 3. That means we're going to multiply 3 to just the x. So what we would want to type in is g of x. Why is it g of x? Because they're calling it a function g for this changed version. So g of x is equal to 7 to the 3 times x plus 1. Nothing's going to change to the plus 1 because we want to do a horizontal, and that means it's just going to apply up here where our x is. Okay, that's it for today. What I want you guys to do today is today's mastery test. Everything we did today covers everything you'll be exposed to in the mastery test. And we've done 6 of those problems already. So feel free to use that if you get one of those problem questions. Just a quick reminder, if you haven't done them already, we need to catch up on the earlier work from this week. And so I didn't put it in here. So here's the full list. What we did Tuesday was page 11, just those 4 questions. Make sure to hit submit at the very end so I can see your work. And then we did the first mastery test, and now today, Thursday, it's the second mastery test. It's called transformations, transforming exponential functions. Okay. I'll put a reminder out this afternoon on the chat for people who are on my Remind. And if you aren't on Remind and you want to be, please give me a shout and I'll be happy to help you do that now or this afternoon. Just let me know. I've tried to add all of you. So if you're not on Remind, it's because you haven't accepted the invite, basically. Any last questions about